What's up, Chem Peeps? What in the heck are we gonna do in this vid? We're going to explain how the strength of an acid or base relates to the equilibrium constant K. Okay? Specifically though, in this vid, we're gonna take a look at weak acids or bases. So we're going to first explain which species are in large concentrations for a weak acid or base. Dos, we're going to explain how to calculate the hydronium ion or hydroxide ion concentration for a weak acid or base. Throughout this vid, I want you to think about how do weak acids and bases contrast with strong acids or bases. Okay, so first thing to recognize is that a weak acid or base does not completely ionize. Usually we're talking much less than 10%. Now, this provides us for some unique and very different characteristics for weak acids. One, recognize that the equilibrium position is going to lie very far to the left, to the reactant side. And because of that, we're going to have very small Ka values. Because the reactant side consists of mostly intact molecules and not ions, weak acids are typically very weak electrolytes. And then finally, bonus for you, there's no set of weak acids or bases that you have to memorize. The vast majority of acids and bases are weak. So as long as you can identify and recognize those very few strong acids and bases, then you can generally recognize everything else as being a weak acid or base. Take a moment, pause the vid, take a look at those images on the screen and in your notes, and think about how they differ from a strong acid that you saw earlier in the notes. Okay, so really important as we tie this into equilibrium to recognize that for weak acid reactions, your Ka expression is given to you on your screen there. Products over reactants. Again, water isn't included because it's a pure liquid. And then recognize that the majority of what you have in solution for weak acids are your original acid molecules. Very little of it has ionized to form hydronium and the conjugate base A-. And because of that, your K values, your Ka values are going to be much less than 1. Really important concept here with weak acids and bases. So in solution, as you look at a particulate representation, notice that majority of what I have are those original HA molecules. Very little of it has been ionized in solution. And then important, recognize that's a dynamic situation. There's this constant back and forth between weak acid forming hydronium and conjugate base, and the reverse, where hydronium and conjugate base reform the original weak acid molecule. Dynamic situation. So, also really important to recognize then is that the hydronium ion concentration is going to be less than the original concentration of the weak acid. And therefore, you cannot just use the Stoic ratio as you would in a strong acid or strong base. And therefore, in order to determine the amount of hydronium ion and therefore the pH for weak acid solutions or weak base solutions, you have to return to your understanding of equilibrium and utilize ice tables. So as a generalized example, take a moment to throw back to the good old days of ice tables. For many of the weak acids that we're going to be working with, it's going to be a 1-to-1-to-1 relationship in terms of the change that we see in our ice table. And additionally, and really importantly, many times the Ka values that we're going to be working with are going to be very, very small. And because of that, we'll be able to perform the X is small approximation to simplify the math in many of the pH calculations that we're going to do. The change that we're going to see in the concentration of the initial weak acid concentration is not going to be substantial enough. So this X is small approximation is really going to come in handy for a lot of what we do in this unit. Take a look at some of those guided practice problems to get you more familiar with how we're going to use weak acids and weak bases in this unit. Done.